Let's get started. So we have everything that you need for homework 4. So let's get started. So you have everything that you need for homework 4 to be able to do the whole homework. We have another week of content. Let me pull up the schedule actually, just for context. So we have another week of what's in homework 4 material. I mean, I guess not the web frameworks at Project Hub. This HTTPS and encryption. So I'll still cover this stuff. This is content that, you know, someday will probably be part of homework 4. It belongs in homework 4. I just don't have a good way to have it in the assignment. It's just not part of the assignment yet. I actually had this in the assignment the first time I offered this course, and it's just, I don't know, it didn't have the educational value that I wanted it to have you host your server as HTTPS. It just wasn't doing what I wanted it to do, so I removed it from that homework. It's one of those things where it's either I make you go from the RFC and build HTTPS from the protocol, like I do with a lot of other protocols, and the homework's nearly impossible, or that objective at least, or I let you use a library and that objective is completely trivial and just takes one line in any language. You just generate your certs and just slap your certs on there, which I didn't see the value in that because you just cut and paste commands and pasted one line of code, and it was HTTPS. I don't see the value in it, but I still want to cover the content. You'll get the concepts. The material will be out there, but you won't have to code this. I hesitantly say that because, when I say things like that. But if you are, stressed out at the end of the semester, just to let you know, this is good content that you don't need for that homework. And then the rest of so I did officially cancel this. I think I did this silently. Next Monday's lecture canceled. Let's just take the whole week off. Let's forget about next week. I think fall recess should be a full week. I don't know why they insist on having us come in Monday, Tuesday. Any class with labs or recitations, it just jacks everything up anyway. I can't do anything with that week. I just got that one lecture on Monday, and let's just not. And then the rest of then a week of just examples. During this week, one of the big things I like to do is take an app and show you how to deploy it, how to get that out there on the internet with a domain name, with a valid certificate to get HTTPS, and just going through that whole deployment process. And then presentations. I have to have a way to sign up for times for project presentations. So that's where we're at. We're really in the home stretch for this course. So let's talk about encryption. So when you send your passwords over the internet, so we know never store passwords in plain text. We salt, we hash. When you send your passwords over the internet, they're sent in plain text. All HTTP traffic is plain text. This includes your passwords. My question to you is, and everybody can read these. Let me make this point first. So who has access to that? So your password's flying around in plain text. Who has access to that password? Every frickin' person in Wi-Fi range of your device. Wi-Fi is not a point-to-point system. It's not like a laser flying over to wherever our access point is, probably in the hallway, I think, in this room. There's one right there, actually. It's not like shooting like a laser to that. It's broadcasting in every single direction, and then the access point knows to listen for that traffic and do what it needs to do, route it through the internet, through the network, and then eventually the internet. So any one of you on your laptop's network card is doing the same thing. It's listening to everything going through the air, everybody's traffic, and then just filtering out the traffic that's made for your device. But you can read all of that traffic. You can see all of the traffic that's flying through the air. Everybody's traffic. So everybody who's on Wi-Fi right now, you can see their packets, their IP packets flying through the air. You can download a program called Wireshark, is the most famous one. Where you download it, and it just shows you all of the traffic flying around in the air in Wi-Fi. So if our passwords are in plain text, and everyone in Wi-Fi range can see that password, of course, a lot of other people have access to, but these are less scary. We tend to trust these people. But if everyone in Wi-Fi range can see those packets, holy crap, they can just steal our passwords.
So when you say Wi-Fi range, do you mean like you have to be logged into the Wi-Fi or just physically in the Wi-Fi range?
It's physically in the Wi-Fi range.
Okay, so like if there was like a Wi-Fi that had a password, for example, I could go physically in the range and see traffic from other users?
Yep, without the password. Yep. I'm like, actually, let me hedge that a little bit. I'm like 95% sure, I'll say. I'll hedge that a little bit. I don't think there's any extra layer when you log into the Wi-Fi. Because those packets have to be going through the air. You can definitely read the packets. I know that 100%. You can definitely read the packets. Whether there's an extra layer of encryption when you log into certain Wi-Fi networks, there's a possibility. I'm not 100% on that one. So you might be reading encrypted packages. In fact, that's the point that we're going to make. There's at least one layer of encryption. We're just going to slap an S on HTTP and encrypt everything. This is our answer to how we're going to protect our passwords and why, when you're on Wi-Fi in a public area, that you can log into anything. It's because we're going to slap that S on HTTP. And I'd like to do a little thought experiment. Why is your password sent in plain text? Anybody have, does anybody have a website where you have to log in? We'll take any website. I'll take any website at all with a login, and I can like 99% guarantee that it's sending your password in plain text. Yeah.
Roblox.
Roblox? Is it just roblox.com? I'm going to open up my browser console. I'm going to go to network. I'm going to go to login. Type in my password. I'm going to log in. Pick the horse. I got you. All right, I'm not going to keep going through that. So let's take a look at our network tab. I got this login request for, where's my, how do I resize you? So I have my request. So there's like one pixel on this where I can grab this and resize. I'm missing it. Anyway, Roblox, www.roblox.com/login, just like your homework, typically /login. Luckily encrypted, that's the big point that we want to make here. But if I go down to the content of this message that I sent, is this, that might be for the HTML. Yeah, that's for the HTML. Where's my post request? Where's my AJAX request to log in? Auth to login. So if we go to the content of auth.roblox, v2/login, they're on version 2 of their login, their authentication part of their server. I can see my plain text password in the payload of that message. So the body of this HTTP request is a plain text JSON string with my plain text username and password. You can do this with any site. I've only found one site, one part of one site where this demo actually failed during a lecture. And I was a little embarrassed, but very, very rare. Almost every app is going to send your password in plain text. Why? For example, why not hash it first? This is quite universal. So if we know hashing adds security, why not hash it? Good answers. Yes. Yes.
Well, if we can protect like the request payload with HTTPS, doing that computation through JavaScript isn't really necessary. Like it would be easier to do on the server.
Sure. It's not necessary. So HTTPS is what's protecting your password. So I can see the plain text in my browser console, but before this request leaves my device, it's being encrypted, and then when it's flying through the air, it's encrypted. So you can still intercept this packet, but you won't be able to see the payload. You're just going to see a jarbled mess of encrypted stuff. So you're not going to be able to read that plain text password. And then it gets to the server, it's decrypted, and the server is handling your plain text password still. Just like at your servers for the homework, you're handling plain text passwords, and it's up to you to securely store them. But this is common. Like once this makes it to the server, that server-side code is handling my plain text password. Like those passwords are exposed at certain parts of the authentication process. For example, like if an attacker attacks a server and gains complete access, complete control over that server, they can just view all the requests coming in after they're decrypted. They can inject some code in there to be able to read those passwords, and they can grab plain text passwords, and they can attack anybody who's actively using the site, actively logging in. They can't attack every single user who ever created an account, but an attacker can still make a, I'm blanking on the word, a live attack, I think we call it. But they can attack users who are actively logging into the site still. That's still, any developer who works at the company who's a little malicious can add their one line of code to be able to grab those plain text passwords right at that moment. So my question is a little misleading. Why not hash these before we send them? The real question to ask is, why would we? Why would we? What's the reason to hash them? And there is no effective reason to hash them. So say I do hash this password and then send it, and I send a hash to the server. That hash of that password is now effectively my password. I didn't gain any security, I just changed what my password is. Instead of not my password's going to be some hash, some SHA-256 hash or whatever hashing algorithm I'm using, and that's effectively going to be my password. It will be longer if I take the full hash, but it won't have any more entropy because once the user looks at the JavaScript and understands what's being used, the one site that I saw doing this used MD5 hashing. And once I see that code in the JavaScript, which I just looked through the JavaScript and found out, that's part of my brute force attack. I just take the MD5 hash, and then I take whatever hash is happening server side, and that's how I attack the password. So I can brute force that. An attacker can brute force that once they know what the hashing is. So it doesn't add any security. It doesn't do anything for us. So why do it? It doesn't help. It doesn't add security. Plus, how are you going to do your password strength checks server side if you have a hash and you don't know what the original password is? Are you going to brute force that password to figure out what the plain text is, to figure out if it's a strong password or not? Probably not. It's a pain in the ass. So we're just going to send the password plain text, do our checks, then hash it before we store. If you find a website, if you do go around and find a website that is hashing first, I'd like to know. I always like seeing examples of that. I like having examples of all these things out there if somebody's not doing this. The one that I found was Bank of America's mobile app. So if you watch, they're going to not do it anymore. I'll do this. This is worth talking about, actually. So if I go to log in, I can look at my request. My goodness. I'll eventually find the right one. I don't think this is it, is it? Yeah, it was this one. Maybe this is the hash right here. Should be plain text on this example. Goodness, why is this so huge? Bank of America, I don't know who you hired to do this. There it is, plain text. So there's my password in plain text. But if we go back, if you notice, when I resize this, and this is the part I want to talk about more so than the security part. If I resize this, at a certain point, the page is going to change. This is how a lot of responsive websites work, is they read the screen size. If the screen size is small enough, they're going to take you to the mobile version of their app. So the screen size is small enough that I'm on the mobile version. And now if I log in, for some reason on the mobile version, do I have a preserve log on now? Maybe they stopped doing it. Maybe my one example is gone. But I've seen before, I don't want to waste more time on this, but they were using an MD5 hash, taking the hash, and then sending that password over the internet. So for what it's worth, if you're on desktop and you want the mobile version of the app, I guess, I don't know why you would, but you can resize or actually use the mobile feature of the browser console. I mean, unless they finally did stop doing the MD5 hashing and got rid of my one example of why are they doing this, you can play with that some more and find out what exactly you have to do to get their hashing. All right, anyway, so the solution to protecting those passwords, slap an S on HTTPS and call it a day. Done. Easy as that. So what HTTPS stands for is HTTP over TLS. You often hear it just called secure HTTP or HTTP secure. But fundamentally what it is HTTP over TLS. So what does that mean? Do I not talk about that? Oh, no. All right, well, I'll just have to explain it verbally. So we have I swear I have slides somewhere. Apparently it's not in this lecture. Maybe it's in Wednesday's lecture. If it is, I'll just explain it twice. So HTTP, actually, yeah, it is in Wednesday's lecture. So let me just do it really briefly here. HTTP over TLS is your HTTP app runs exactly the way it is. Everything you wrote for your server that runs off of HTTPS, everything there works exactly as you wrote it. You don't have to change anything to use HTTPS. Where you do make a change is in your TCP socket. Right in between your TCP socket and your HTTP server, you're going to add this layer of encryption called TLS. So this sits right in between those two in the network stack. So whenever you send information over the TCP socket, you're going to encrypt it first and then send it over the socket. So instead of just send bytes. And in most libraries, that's part of the TCP library itself. You say, hey, TCP server that I'm starting, use this TLS encryption, use this public-private key pair, and do your encryption thing. And then whenever you send messages over that TCP socket, it'll just be encrypted. And you don't have to think about it in your server side. When we're building web apps, we want to focus on the app, the features of the app. We want to be thinking about security at the same time with features. So we have this nice encapsulation. TLS is just going to be a separate layer sitting right in front of the TCP socket that's going to encrypt and decrypt everything that comes in. Yeah.
So would we also have to do that for WebSockets?
Yep. So your TCP socket server would handle all the encryption. So since your WebSocket connection is still using that TCP connection, it's going to be encrypted. Okay. And then so the WS protocol will be WSS.
Right. So would the frames themselves be encrypted or just the socket?
Everything that goes over the socket. So you would build the frames just like you do now, except when you say, hey, TCP socket, send this frame over, the socket's going to be, the TLS is going to encrypt and then send it over the socket. Well, anytime you say send bytes or receive bytes, send is going to encrypt and receive is going to decrypt. So for encryption, we have some plain text message that we want to hide. We don't want people knowing this. Could be anything that we can encode in bytes. And then we're going to encrypt it into what we call ciphertext. Ciphertext is what we're going to send over our insecure channels, the channels where we might have some attackers, some eavesdroppers, some man-in-the-middle attacks, whatever. We're going to send the ciphertext over that channel. Anybody could be sniffing packets out of the air here. Send a ciphertext, so all they get is a ciphertext, but we want to send that in such a way that the intended recipient can still decrypt into the plain text message, and ideally only the intended recipient. They're the only ones who can decrypt. This is what that looks like. In practice, if I want to send this message, I'm going to encrypt. This is what it's going to look like as it's thrown, flying through the air. And then the intended recipient can decrypt this and get back to the original message. So that's our goal. We're going to achieve this through public key encryption. This is a crypto system that works off of a public key and a private key pair. So we're going to generate a pair of keys such that the public key, you guessed it, is public. We're going to share that with absolutely everybody. Every single person on the planet can have our public key. No big deal. You just hand that thing out like candy. Here's my public key. Everybody can have that. Private key, you guessed it. Keep that private. You put that in your pocket and you don't tell anybody about that private key. Nobody gets to know about that private key. Whenever you want to send a message to me, say I generate this public-private key pair, I share the public key with you, with everybody. You want to send me a message, you're going to encrypt with my public key. Send me the message, I'm going to decrypt with my private key. So this is the feature that we want for a public key encryption system. Encrypt with the public key such that only the holder of the private key can decrypt that message. That's our goal. If I want to send a message to someone else, I'm going to encrypt with my public key, and also we're going to, I think I talk about it later, but I could also encrypt with my private key such that people can decrypt with my public key. Everybody can read that message, but it's a digital signature, which means I prove that I wrote that message because I encrypted it with my private key. So whenever you see digital signatures, that means somebody took their private key, encrypted, and then you can decrypt with the public key to verify that I am the author of that message because it was clearly encrypted with my private key. Yeah.
So how would, you send a message that you encrypted with your private key. What, the public key, you use it to decrypt. What are you seeing? Are you seeing the content of the message, and then how would you know that it was you who did it?
So with digital signatures, usually you send the message in plain text, and then also a digital signature at the end to verify. So you would read the message and then decrypt the digital signature to verify that it was me. Yeah, or else if it just so happened to decrypt with the wrong public key to a valid message, how would you tell? I think is your question, right?
Yeah.
How would you tell if this is the actual message? Who knows? That's why you send it in plain text and then sign it. So there's two big properties that we want from public key encryption. An attacker, since the public key and private key are inherently related, they're mathematically related. They definitely have properties that make them linked together. So given that fact, an attacker with the public key should not be able to determine what the private key is, and an attacker with a ciphertext should not be able to figure out what that text is. And keep in mind that they will have the public key because it's public, so they have ciphertext and public key. With that information, they shouldn't be able to decrypt or figure anything out about the properties of the private key. So the one public key encryption scheme that we're going to look at is RSA. And that's going to give us everything that we need. We're going to talk about how to generate keys, encrypt, and decrypt. And I'm going to hit you with some math. Key generation is this. And that's it. It all fits on one slide. This is how we generate keys with RSA. So let's step through this one step at a time. We're going to we're going to choose two very large random prime numbers, which we'll call P and Q. We're going to multiply them together to formulate N. We're going to take the least common multiple of P minus 1 and Q minus 1, call that lambda of N. We're going to choose some E with the properties such that E is less than lambda of N, and E is co-prime to lambda of N. So the greatest common denominator between them is 1. When that's a fact, we call that co-prime. So there should be no common factors between them. And then finally, compute D as the inverse of E modulo lambda of N. If you do this, you share both E and N as your public key. Keep D as your private key, and throw everything else away. And you've just generated your public-private key pair for RSA.
When you say large prime numbers, like what would you define as large in this scenario?
Like they should take thousands of bits, like multiple. We measure the key sizes in like 2K, 4K, like thousands of bits to represent the primes. So like P and Q log 2 should be thousands. Big stuff. To encrypt, take your plain text M, raise it to the power of E mod N, and that generates C, your ciphertext. To decrypt some ciphertext C, raise it to the power of D mod N, gets you back to your plain text M. The way all the math works out, M raised to the E times D power mod N is going to give you M back. So if you raise it to the power of both E and D, the public and private key, you get back to the original message. So this is where our digital signature comes in. Since multiplication is commutative, we can do this in either way. We can either raise it to E first or D first, and each of those operations is going to encrypt or sign in such a way that raising it to the power of the other E or D mod N is going to get us back to the original plain text. So if we do this the other way around, encrypt with the, or sign, it's technically not encryption, sign with the private key, we get that digital signature, and the math all works out because this multiplication is commutative. Doesn't matter which order we do this in. There's a big problem here. A few big problems we'll go through. So why not just brute force encrypted messages? Everybody has the public key. Why not do the same thing that we did with the hash function? Take the public key and continuously so somebody encrypted with the public key and sent a message to me, and I intercept that ciphertext, and I want to figure out what it says. I have the public key. Let me just keep guessing what the message is and encrypting with the public key until I guess right. Once the ciphertexts match, I just broke the encryption. I just broke it. I read your message. I recovered the ciphertext. So why not do this? We did it with hashing. Why not do it with encryption? We have all the tools in our toolbox to be able to do that, or the attacker does, rather. Why not? So we can, but luckily we have a way to mitigate this risk. We're going to use a padding algorithm. So a padding algorithm, what this does is when I have a message to send, I'm going to take that message, generate as many random bits as I want, a long, random chunk of information, append it to the end of the message, and then encrypt. Now if somebody wants to guess that message, they have to guess all of those random bits. And I can add as many as I want. I can get as much security as I want out of this, as much entropy as I want. At least 80 bits if we want to get over that threshold, but why not hundreds? Why not hundreds of bits? We can do as much as we want, depending on our application, our trade-offs with efficiency and everything. We're going to add as many random bits to the end of that. This does add entropy, it does add security, unlike salting. This does add security because every single one of those bits has to be guessed in order for somebody to brute force this thing. So they have to guess every single one of those bits and the message. And at that point, there's probably a lot of different combinations that, let me not go there. But this does add security, it does add encryption, and it doesn't interfere with the usual operation of things because I decrypt that message when I get it, and there's a few bits that say there's this many bits of padding. I read that many bits of padding, throw it away, and just read the message. Even if we want to send one bit of information in our message, we add all this padding, and it can't be brute forced. Within, not until the sun burns out. Nobody's going to decrypt that thing. I'm going to do my demo right here. So I have some encryption in, oh no, don't want that. In Java, I'm going to encrypt with RSA. I'm going to generate a pair of keys. I'm going to encrypt. I'm going to decrypt. And I'm going to use that example from the slides, meet us at the stick. I'm going to generate my keys, get the private key, get the public key, encrypt with the public key, encrypt again with the public key, print out both ciphertexts, decrypt with the private key, decrypt with the private key, and then print both of those out. So let's run this thing. And we decrypt to the same message both times with both ciphertexts, but we can see that both ciphertexts, since we'll get different padding each time, completely different. So even if we keep sending the same message, maybe we have one bit of information, we keep answering yes to a question on a form or something like that. We keep saying yes, 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 yes. The crypto text each time is going to be significantly different every time. So the attacker doesn't get any information. It doesn't get, oh, you just sent, I don't know what this message is, but you sent the same message over and over and over again. With the padding, nope, no go. Crypto text completely different every single time. They're not getting any information out of this. Cryptography is extremely strong. Like hashing had all kinds of problems with entropy and things like that. Cryptography does not have those same problems if used properly. If you're using a proper padding algorithm, for example. In this example, if you're not using padding, you might as well not be using encryption because you're doing it wrong. So we use a padding algorithm, gives us lots of good properties, lots of nice properties from padding. Okay, the next problem, if we look at this generation, the key generation, everyone has E and N. If I just take N, and I know it's the multiplication of two primes, if I factor it into P and Q, I have absolutely everything that I need. I can compute lambda of N, I already have E, and I can compute D the same way that we computed it during key generation. All I have to do is factor N, and I have the private key. So given a public key, E and N, factor N, and we're home free. That's it. That's all an attacker has to do to break this encryption scheme wide open. So that seems like a big problem. But luckily, as it turns out, factoring is a really hard problem. It seems like a simple thing. We did it since grade school. You factor, do prime factorizations all the time in grade school. It's not that hard to do. When the numbers are small, we can do it as humans. We can just say, oh, it's even, let me divide by 2, and just kind of brute force it. But to train a computer to factor efficiently, extremely difficult as it turns out. At least we hope it is. Nobody has proven mathematically, like a 331 style proof, that factoring is hard. Nobody's given an algorithm, or at least publicly announced that they have an algorithm that factors efficiently. And we're kind of leaning on the idea that factoring is hard. Like the whole crypto community is really hoping that factoring just is hard. This is what we call a cryptographic primitive. We start with the assumption that factoring is hard, and if breaking your encryption scheme means not breaking factoring, but having an efficient factoring algorithm, then we're going to say that that's secure. It boils down to, it reduces to a cryptographic primitive, so we're good. And there are more cryptographic primitives. Factoring is just one of them. Now we're using elliptical curves that seems like a better, can I even say that, a better primitive, properties of elliptical curves. Factoring, if quantum computers get practical, Shor's algorithm is going to blow apart factoring. So we don't want to rely 100% on that, because if Google gets their quantum computers running, crypto's done if it's all relying on factoring. So we do have other primitives, but factoring is the one that RSA, the way we've seen it, is based on. So it turns out this is really hard. If you can factor efficiently, especially when n is the multiplication of two primes that are thousands of bits long, if you can do that efficiently, you'll break RSA.
Oh, yeah, that was just my, that's why we make the primes so large, is to make factoring.
That's why the primes have to be so large, yep. If the primes aren't large, you'll break encryption. Or you don't have any security, I should say. So the primes have to be large. Okay, there's another problem here. This is the last problem that we have with RSA itself. When we compute C, if we want to get back to M, we have E. We already have that, it's part of the public key. We have N, that's already part of the public key. We have C, that's the cryptotext that we grabbed from the air. So all we have to do now is compute the discrete log base E of C mod N. So if we compute the log, like if you ignore the mod N, this would be the log base M of C would equal E. So with the mod, we have to compute the discrete log. We have to do the same kind of idea, but in the world of modulo. So we had to do the discrete log modulo n. So if you can compute that, you blew this encryption scheme wide open again. So either factoring or discrete log. Luckily, discrete log is hard also, we hope. This is another cryptographic primitive, luckily, or else RSA wouldn't ever be used. So this is another cryptographic primitive, computing discrete log. Turns out to be really hard to do. Seems like a fairly straightforward mathematical thing, factoring and discrete log. They're both extremely hard when the numbers get large and we don't have any efficient algorithms to compute them. I already did the demo. I want to get into anybody have any questions about this? Goodness, they're so loud out there today. Eight minutes, sure. Let's keep going. Let's do all this. So there's another problem. This isn't a problem with RSA itself, but in the way that we implement encryption out there in the world, called the man-in-the-middle attack. This one's pretty devastating. So to create an HTTPS connection, the very first thing that has to happen, I shouldn't say the very first thing would be the TCP three-way handshake. But after that, the server needs to send me its public key. I need that public key if I'm going to encrypt anything. If I want to encrypt and send something to the server, I need that public key. I need it. So what if somebody's in the middle of this communication and intercepts the server's public key and replaces it with their own? So they're in the middle listening to all this communication. They see that I requested the public key. They get the public key from the server, replace it with their own, and I get an attacker's public key. Now every time I send a message to the server, the attacker decrypts it because I encrypted it with their public key. They have the private key. They're going to decrypt, read the message, do whatever they want with it, and then depending on what they're trying to pull off, they could change the message, encrypt with the legitimate server's public key, and then send their message on my behalf to the server. So now I think I'm communicating with the server, but I'm actually communicating with the man in the middle, the attacker, and the attacker is communicating to the server on my behalf with whatever messages they want to send. Usually, one of the first things you do when you connect to a server, you're going to say, here's my username, here's my password. So if somebody successfully pulls off this attack, they're probably just going to intercept that, get your plain text password that they decrypted because you encrypted it with the attacker's public key. They get your password, and they can just run away after that, sever the connection or whatever, and then you'll get some like a 404 or 403 or whatever. You'll reconnect with the server legitimately, and you won't really think anything of it. But you've just been attacked, somebody stole your password, and they can do whatever they want to do after that. These are all bad things, of course. So the solution to this, certificate authorities. And this, I'll have more of a demo on this on Wednesday. We're going to run out of time for the demo, but I'll get the groundwork down. So certificate authority is a known, trusted source of encryption. Is that the right way to word that? But they're known public keys. So they have their private keys, and they have known public keys that they distribute through means that we assume are secure. This is when you install your operating system, when you install your browsers, they're going to add keys to your machine's keychain, which are going to be assumed, trusted, public keys that we assume there was no man-in-the-middle attack. We trust these keys from the certificate authorities. All security, all encryption, everything does rely on the assumption that something was secure at one point in time. You have to have some secure communication to begin with. This is the root of all encryption on the internet, is the assumption that we receive the certificate authority public keys securely, that those are actually the CA public keys. If they're not, then there's no encryption, there's no security at all, anywhere on the internet. So we assume that these certificate authority public keys are securely delivered to us through installation processes, not over networks, though we also download browsers through the internet. Like at some point there has to be an assumption of security, which is something to think about, like what can go wrong. This is why when you download things, a lot of times there's the MD5 hash of the file. You should hash that file when you receive it. You could, if you want this extra step, download the browser, installation, executable, whatever disk image, whatever it is that you downloaded for your operating system, hash it, and then make sure the hash matches what you have on the website. And then make sure that website didn't get attacked and replace the hash. Like you can keep going down the rabbit hole. At some point, you have to assume that something was secure. What if you already had a man-in-the-middle attack who replaced that hash on the website? I don't know. At some point, you have to just make an assumption that you're secure. So we have these certificate authority public keys. The certificate authorities are going to issue certificates to all the domains. So if you buy a domain name, you go to a certificate authority, you say, hey, I need a certificate for my domain name. That certificate is going to be your private key, your public key, signed by the CA's private key. So the CA is going to sign your public key. You sign your certificate, which contains your public key, and then you distribute that certificate. If that certificate is replaced by an attacker, it's not going to have a valid CA signature for that domain name. So if I go to google.com, I'm going to get a certificate that says this is the public key for google.com, signed by whatever certificate authority, which Google signs its own certificates, I believe. I'm going to get that certificate, and if there was a man-in-the-middle attack, that won't be a valid cert because no CA is going to issue a certificate for google.com if it's not actually google.com. They can't get those certs. And to spoof a cert, they'd have to break encryption itself, the signature. They're not going to be able to break that. And certificate authorities have very large keys that you're not going to be able to brute force. So you get that certificate, you take your public CA key, You verify the certificate, and then if it's a valid certificate, then you have the valid public key for that server. If anything goes wrong with that process, your browser yells at you and says, whoa, this isn't secure, we couldn't verify anything, maybe get the hell out of here. Which you've probably seen before. Sometimes even legitimate sites have that happen every once in a while. The certs have expiration dates. If they expire and the sysadmins didn't update didn't get new certs yet, you'll get that for a little bit until somebody panics. I've done this before with my servers, speaking from experience, where you panic and go, oh shit, my cert expired and I didn't renew it. You renew your cert and then that warning goes away. So for this, the CA is signing it and taking a hash of that signature. We get to combine cryptography and hashing. I already said all that. I'll do the example next time. But the CAs themselves, the root CAs that are installed on your machine, rarely issue certificates themselves. What they do is issue certs to other CAs, non-root CAs, and then those CAs might sign for other CAs, which finally sign for domain names. So you end up with is a key chain. From the cert of the domain that you're visiting, you should be able to find the cert for a CA, which was signed by a CA, which was signed by a root CA. As long as eventually that chain leads to a root CA, you're secure. We're going to say that's good. Yeah.
So like every browser has the same root CAs, typically?
Has the same CAs?
Like root CAs, like when
Yep.
you install?
Yep. Yeah, between operating systems, browsers, everything, the same root CAs, same group of them.
Is that information like publicly known, or is like
Yeah.
the browser have to request it? Because if they could go, if I could go and find those root CAs, couldn't I go through the chain to get certificate like?
You wouldn't be able to.
Oh, but I wouldn't.
You wouldn't be able to generate because you don't have the CA's private key, so you can't generate those certs. But you have their public key, so you can verify a cert.
Yeah.
All right, see everyone Wednesday.